Hey, if you've ever stared at a chaotic string of letters and numbers in algebra and just felt completely overwhelmed, trust me, you are not alone. Today, we're jumping right into the foundations of Class 10 polynomials. We're going to uncover the hidden structures and, honestly, the beautiful logic behind all of it.
Now, why should you care? Well, the stakes are pretty high here. Mastering this can literally secure you up to 7 board exam marks and totally unlock the door to high school algebra. Seriously, this isn't just boring theory. These are the exact concepts that translate into high scores and make everything you learn next year so much easier. And you know what? It's actually incredibly straightforward once we start visualizing it together.
Here's our roadmap for this explainer. 1. The polynomial foundation. 2. Discovering the zeros. 3. The secret relationship. 4. Building and dividing. And 5. The big picture. Let's get into it. Section 1. The polynomial foundation. Setting the rules. Okay, first things first, we gotta know how to spot a real polynomial. We have the valid ones, like 3x squared plus 5x minus 7, or even just the number 7. But then look at the other ones. These are total imposters. 1 over x, the square root of x to the power of -2. Yeah, no, these are absolutely not polynomials. Why? Well, it's the ultimate unbreakable rule of this math club. The powers of your variables must strictly be non-negative whole number integers. That instantly disqualifies any fractions, like the half power hiding in a square root, and it completely bans negative powers. If it doesn't have a clean whole number exponent like 0, 1, 2, or 3, it's out. Now, let's talk about the degree. This is simply the highest power of the variable in your equation. Think of it as the polynomial's identity tag, okay? It literally tells you everything about how that equation is going to behave. And this identity tag tells us exactly what kind of mathematical beast we're dealing with. If the degree is 0, it's a constant, like the number 5. If the highest power is 1, it's a linear polynomial. Think 2x plus 3. If that highest power hits 2, well, that's a quadratic. You're going to see a lot of these, like x squared plus 5x plus 6. And if the degree is 3, it's a cubic polynomial. So just by spotting that degree, you instantly reveal the true nature of the equation. Section 2, discovering the zeros, finding the magic numbers. All right, let's figure out how to find the value of a polynomial. The logic here is incredibly simple. You literally just plug in a number. Let's say our polynomial is x squared plus 3x plus 2, and we want to find its value when x equals 2. We just swap out every x for a 2. So 2 squared is 4, plus 3 times 2, which is 6, plus that last 2. 4 plus 6 plus 2 equals 12. So the value of this polynomial at x equals 2 is 12. Super easy, right? But what if you plug a number in, and the final answer isn't 12 or 5 or -10, but exactly 0? Well, when that happens, that number gets a very special title. It's called the zero of a polynomial. For instance, if you have the equation x minus 5 and you plug in a 5, the equation becomes 5 minus 5, which equals 0. Therefore, 5 is officially the 0. It's basically this incredible magic number that completely neutralizes the whole equation. So, understanding this algebraically is absolutely crucial. But let me ask you this. What do these zeros actually look like on a graph? Let's shift gears for a second, moving from abstract algebra into visual geometry. This is where things get really cool. Geometrically speaking, the zeros of a polynomial are exactly the coordinates where the graph cuts directly through the x-axis. Literally, that's it. If you have a linear polynomial, which always forms a straight line, it cuts the x-axis exactly once, meaning it has 1 0. But a quadratic polynomial forms a U-shape, also known as a parabola. Depending on where it sits on your graph, that U-shape might cut the line twice, giving us 2 zeros. Or it might just barely graze it once, giving us 1 0. Or it might just float way above the line and never cut it at all, meaning 0 real zeros. The algebra perfectly matches the geometry. It's like a giant puzzle coming together. Section 3, the secret relationship, the cheat codes. Okay, I need you to pay very close attention here because this is literally the ultimate cheat code for your exams. There is a permanent hidden link between the zeros of a polynomial and its coefficients, the number sitting right in front of the x's. For a quadratic polynomial in the standard form ax squared plus bx plus c, if you add the two zeros together, let's call them alpha and beta, their sum will always exactly equal -b divided by a. And if you multiply those two zeros together, their product will always equal c divided by a. Guys, we don't even have to graph anything or solve the whole complicated equation to know exactly how the zeros behave. Don't believe me? Let's prove it actually works. Take the equation x squared minus 5x plus 6. Here, a is 1, b is -5, and c is 6. Using our cheat code formula, the sum of the zeros should be -b over a. So -5 over 1, which is +5. The product should be c over a, which is 6 over 1, giving us 6. Now, if we actually did all the long math to find the real zeros of this equation, they turn out to be 2 and 3. Let's check the math. Does 2 plus 3 equal 5? Yep. Does 2 times 3 equal 6? Absolutely. The cheat code works every single time. Honestly, it feels a little like magic, but nope, it's just solid math.
Section 4. Building and dividing. High-level math.
So, because we know that secret relationship, we can actually build a polynomial totally from scratch if someone just hands us the zeros. The template is crazy simple. It's x squared minus the sum of the zeros times x plus the product of the zeros. Let's say someone tells you, hey, the zeros are 2 and 5. Well, the sum is 7, the product is 10. So you just drop those numbers right into the template. You get x squared minus 7x plus 10. Boom, you literally just built a quadratic equation in your head. Now what about breaking them apart? Well, it turns out dividing these equations uses the exact same logical process as that long division we all learned in elementary school with regular numbers. The old rule still applies. Dividend equals divisor times quotient plus remainder. So if we divide x squared plus 5x plus 6 by x plus 2, we end up with a nice, neat quotient of x plus 3 and a remainder of 0. See? It operates on the exact same mechanics as basic arithmetic. You already know how to do this. And real quick, I want you to notice how this pattern expands perfectly to higher degrees. If you have a cubic polynomial, so 3 zeros, alpha, beta, and gamma, the formulas just stretch out. The sum of all 3 is still -b over a. The sum of the products of every pair is c over a, and the product of all 3 is -d over a. The mathematical universe is just incredibly beautifully consistent.
Section 5. The big picture, your destination.
Okay, so why does all of this actually matter? Understanding the concepts in this explainer is your foundational key. Think of it as a domino effect. In Chapter 2, you master these polynomials, but if you don't grasp this now, Chapter 3 on quadratic equations is going to be incredibly frustrating. Chapter 4 on arithmetic progressions, that completely relies on this logic too. Later in the term, coordinate geometry is going to require you to understand how graphs and equations interact. And looking ahead to Class 11, higher algebra just assumes you already know all of this perfectly. This is the one domino that sets everything else in motion. So these right here are your must-remember formulas. Seriously, memorize these. Write them on a sticky note, slap them on your bathroom mirror. You've got the quadratic sum and product and the cubic sum and product. These are absolutely the most frequently used formulas in the board examinations for this entire topic. And why exactly should you put in the effort to memorize them? Because these concepts, specifically the zeros, the graphs, and those secret relationships between the zeros and coefficients, are directly worth 5 to 7 marks on your board exams. That is a massive chunk of your final grade, all wrapped up in just a few simple logical rules that we just broke down together. All right, you've successfully mastered the building blocks of Class 10 polynomials. You know exactly how to identify them, find their zeros, map them out geometrically, and use those secret cheat codes. The language of algebra is officially yours to command. So, I want to leave you with this thought. Now that you have these powerful tools in your mental toolbox, what complex equations will you conquer next? Keep exploring, keep questioning, and I'll see you in the next explainer.